Now, with this set of notes, we're going to be starting an entirely new set of considerations. In particular, we're going to begin considering what happens when charges begin to move. So far in this course, we've really been working primarily just with Coulomb's law, if you really think about it. And Coulomb's law, it turns out, is not the full reality of everything. We've certainly used Coulomb's law to bootstrap ourselves into this concept of an electric field and to give some meaningfulness to it, realizing that that's one of the main ways we can get rid of the concept of action at a distance. We've seen how the electric field becomes more and more real to us, particularly as we've learned it can actually store energy and space in this electric field. But all of that ultimately comes down to Coulomb's law. And Coulomb's law, as it turns out, is not exact. And it begins to break down in some important ways, actually, when charges are moving. So we're going to be changing our considerations now to think about moving charges. So far, we've thought about currents and current flowing, and that certainly is going to relate back to this idea of moving charges. None of these new effects that we'll be talking about so far affect any of the considerations that we've dealt with so far in circuits. So everything that you've learned so far turns out to be an extremely good approximation. But there's some new interesting effects that are going to come out of this. Now, the interesting thing is, though, it turns out that by simply knowing Coulomb's law and how that works for stationary charges, we can actually use that physical fact as the basis to develop new theories for these corrections that I'm trying to bring to mind here that begin to occur when the charges are moving. And the way we can do that is by bringing in ideas from the theory of special relativity, which deals precisely with this question of how physics might look different when things begin to move. So the way we're going to introduce the topic in this course now is to give you actually a crash course in relativity. Now, in a course like the one that we're teaching you here, we don't have time to go into a lot of depth into this very rich and deep subject of relativity. We can only really talk about it for about half of a lecture. On the other hand, if you pay very close attention to what I'll be telling you in the next 15 minutes or so about special relativity, you will have the full knowledge of that theory, so that in principle you can deal with any of these questions, these very interesting questions that come up in special relativity, using just what I'll be telling you here. Of course, it generally takes a little bit longer to be able to fully appreciate the consequences of the physical laws that I'll be showing you. And a typical course in relativity might last for several weeks instead of just half a lecture, but you'll have all of the key ingredients, all of the basic physics you'll have at hand. And the final comment I want to make before we begin is we're tying back to something I said at the very beginning of the semester, which is the fact that electromagnetism really was the first truly relativistically invariant field theory. We've already seen the concept of field. We've already begun to learn about field theory in general. We haven't yet seen the power of this idea of the relativistic invariance, and that's another thing that will come out of today's lecture. So, first we'll begin, though, with this crash course in relativity. There are basically 4 things that I want to get across to you that you need to understand the core of relativity. The first thing, it was Einstein's really first basic starting point, and that is the fact that the laws of physics, all the things that we've been learning so far, in fact, are valid and are the same for all observers. So for you, for me, for everyone, right? There's an underlying reality, objective reality out there. Sometimes people confuse relativity with this modern philosophical concept of relativism, right? Where, like, I've got my truth and you've got your truth, and my truth is good for me, yours is good for you, but there's no real objective reality out there. Physics doesn't work that way. Physics is based on the idea of the existence of an objective truth. And one of the reflections of that fact is this, that the laws of physics are in fact the same for all observers. Now, relativity, though, begins to talk about certain types of observers for which we can really understand very well how these laws are always the same. So law of physics are actually saying for all observers traveling at constant velocity or constant speeds or constant velocities at constant velocity. I'll make it at some constant velocity v, right, regardless of the value of v. This should be very familiar to you from your common everyday experience traveling perhaps in an automobile or on a train, right? Even though your car or your train might be barreling very quickly down the highway, right? If you sit in the back seat of your car with a friend, you can simply toss a ball back and forth between the two of you, and all of the normal trajectories that you're used to, all of your, kind of intuitions about how that ball should behave don't change one iota due to the fact that your car is barreling down the highway at extremely constant speed. It's actually remarkable how well that kind of thing works out. Now, so far so good. The thing that's a little bit surprising, that's a little bit different, is that although what I've just said to you is completely true, it turns out that there are some differences. There are some ways that velocity affects things. It doesn't affect the law of physics, but it does affect what observers observe. So everybody who's traveling at a constant speed, all these observers, right, everyone, though, observes events. And we'll talk a little bit what we mean by event, right? They observe these events as occurring, as happening, right, at different times and locations. So there is some difference between what I might see and what you might see. However, again, this is not relativism. There is an underlying truth out there. And the reflection of the fact that there is this underlying truth is that there are very specific mathematical ways that my observations, for instance, of times and locations for events have to relate to your recordings of the different times and locations for those events. So let me get a little more specific here, exactly what I mean by all of these things. So let's suppose, for instance, I observed some type of an event. So what I would do then to make a careful recording of what had happened is I would set up some kind of a coordinate system. So I'm going to have some kind of, Cartesian coordinate system with x and y axes. And of course I'm going to have my little tick marks here along my x-axis. And then I will be standing, say, at the origin of my coordinate system. So here I am, standing there, my professor glasses here, making some observation, and I'm looking out at the world, and I'm kind of observing everything that's going on around me. And now maybe something happens. Maybe there's an explosion occurs. So there's going to be some explosion, say, at this particular location. So I can then make a record of precisely where and when I thought that explosion occurred, and I will call myself here observer number 1. And that means then when I record that event, it's going to occur at a certain location in my coordinate system, which I will call x1. And when I look at my watch, I will see that it occurred at a certain time, t1. All right, very good. Now, let's bring someone else into the situation. Maybe you, right? Maybe you are in that car that was barreling down the highway at high speed. Now, as far as you are concerned, you've got your own coordinate system that's perfectly good for you inside of that car. So let me try to sketch that for you. So I'm going to have, I'll move it a little off center, right, to reflect the fact that it's moving. You too would set up your own coordinate system. Perhaps I should have called this x1 and y1 because those were my coordinates. Here are your coordinates, x0 and y0. And you, of course, are going to be seated in a chair here, right, in the automobile. Your legs there, arms, head, right. You're observing things too. You have your own little tick marks that go with your coordinate system. And this whole thing, you and your coordinate system, and this is kind of key, right? You and your coordinate system are all, traveling together, barreling down that highway at some velocity v. Now, you sit there and you observe, and you're going to see that explosion occur, right? So you're going to observe it, though, to occur. So here I'll try to draw it, right? And when you make the recording of that explosion, you will have your own particular time and your own particular location, x0, say, and time t0, according to your watch, to indicate when that event happened. Now, as I've been saying, right, these things just don't happen willy-nilly, right? It's not like any old thing can happen in your coordinate system and anything old thing can happen in my coordinate system and there's no underlying reality. There has to be a very specific relationship between what I observe and what you observe in order for there to be an objective reality out there. So and what relativity does actually is it tells you precisely what that mathematical map is. So let me scroll up here a little bit, and I will give you the conclusions from special relativity about precisely how these events must relate to one another. So there's a nice formula that's going to tell me what my observation of the location x1 and t1 of these events are going to be. In terms of your observations, remember, you're going to be observer O or 0. Now, it turns out that the most compact way to write this down is as a matrix multiplication. You can write out the separate equations if you want, but I presume that you've all had your Math 1920, so you're familiar with the basic row times column operation of matrix multiplication. It's just easier to write this out in a more compact form that way. So then what I observe then is going to equal some factor gamma, which I will define for you in a moment, times a matrix, which has component elements 1, v divided by c squared, where I'll define c in a moment, but it's the speed of light. And there's another 1 that goes here. And then that matrix multiplies your observations of the event, x0 and t0. Now, to define things carefully, of course, v here represents precisely the velocity v that you, observer 0, are traveling with. x0, t0, x1, t1 I've already defined. The other new quantity here is c. As I've mentioned, c is the speed of light. And that's been measured, of course, extremely carefully. A good approximate value to always keep in mind is about 3.0 times 10 to the 8th meters per second. So it's an extremely high velocity. Most typical velocities that we would observe, of course, are much smaller than that. And then finally, there's the factor gamma. I guess I'll just write down what v is anyway. V is the velocity of observer 0, right? Velocity of 0 relative to observer 1. And then finally, gamma is just a mathematical formula in terms of c and v. It's equal to 1 divided by the square root of 1 minus v squared over c squared. Now, one thing I'd like you to notice, of course, is that typical velocities v are much less than the speed of light. And so, of course, v squared over c squared would be a very tiny number, and then I have just 1 divided by 1. So in most cases, I just make clear that that's a 1 there. In most cases, gamma is very close to 1 in most cases that we're familiar with, until you start to travel near the speed of light. Now, I guess just for completeness, I've told you now, of course, how x0, right, and x1 will relate to one another. I haven't told you about the y coordinates, right, or the z coordinates. It turns out those obey a very simple relationship. If I want to know where I think the y and z coordinates of some event would be compared to what you think, it turns out those we will actually be in complete agreement upon. So that's it. That basically tells you how to map events from one observer's reference frame into another. So this leads to a set of interesting phenomena then that we will outline in just a moment. There's like this time dilation and all kinds of interesting effects that we saw in that wonderful movie Interstellar. But before we get into the exotic effects, let's just try a more simple example. Let's try some simple example. Suppose, for instance, I just want to think about my observation of you, right? So if I think about you, right, then I know that your observation of your own position, x0, right, that is always going to be 0 for you in your chair in your own coordinate system, right? You in your chair. And then if we think, right, you always just look down and see, oh, I'm sitting still. I'm just sitting at my position, x0 equals 0. Fine. But what's interesting is when I apply then this transformation formula, I see that x1, what I think are your locations, I can get by doing my matrix multiplication, right? So I would have a factor of gamma, but we know that's going to be close to 1 under normal conditions. And then it's row times column to get the element of the output. And then the row times column gives me 1 times x0. So I have my factor of gamma I factored out. There's 1 times x0 plus then the next term is this v times t0. But of course, x0 is actually 0 in this particular example, and gamma is very close to 1. And so when I run all this through, all I see then is that my recording, x1, right, that's my observations, when I'm just sitting still, of your location, is that I see it just increasing linearly with time with velocity v. So all that I see when I write down your location is I see something that's increasing with time in my coordinate system at a constant rate, which just simply reflects the fact that we already agreed that you were moving along here with your coordinate system. So all of that kind of checks out very nicely. So that's the basic transformation formula and how it works. Now, as I had mentioned, this can lead to a whole series of interesting effects and paradoxes. And so those then lead to my final 2 items in our little mini crash course here on relativity. So let me slide up a little bit. So point number 3 then, and this is really just a consequence. Everything is a consequence of these transformation formulas in relativity. So the third consequence is that stationary observers, so I'll put that in quotes, right? A stationary observer, because who's to say who's stationary or not? But I mean, in this example, that would be me, right? Standing there, say in the lecture hall, while you're driving by quickly in your automobile. So the stationary observer then sees a moving observer. The moving observer, speaking of moving, sees the moving observer as actually aging more slowly. By a certain factor. And we can see from the transformation of what that factor is. Because in the transformation, you'll notice my times T1, when I do the matrix multiplication, I get that T1 goes like T0, right? Because I'll get 1 times T0. There's also this V squared over C squared thing, but that's going to be V over C squared. That's going to be very tiny, right? So I basically see that T1 is T0, except that there's this factor of gamma that multiplies things. So I'm going to see you as aging more slowly by a factor of gamma. So if I think of an example, and again, you'll see that all the time in Interstellar, how everyone's getting really old back on Earth. Some of that effect was due to gravity, which comes from general relativity, but there were, in fact, cases, I believe, in that movie where you also saw it just from their pure motion traveling near the speed of light. But in any event, that's a known physical fact. It's been observed. People have taken atomic clocks, put them, very accurate clocks, put them on jumbo jets, flown them around the world, and seen the changes in time associated with with this effect, this time dilation. I guess I'll label it there too. Time dilation. Very common effect. So if I want to give you an example, if Sally travels, say at a velocity v equals 0.98 c, and if she does that, right, for 5 years, and notice when I make this statement, I'm saying we see Sally travel at this speed for 5 years. Sally, of course, doesn't think she's traveling, right? She thinks we're traveling. But if we see Sally travel at that speed for 5 years from our reference frame, we observe her, we see her age only about 1 year. And that's simply because if you work through the formula for gamma, you'll get a ratio of about 5 to 1. Okay, well that's kind of neat. But then that leads to a paradox, which then helps explain the other common consequence of relativity, and something that we're going to need in our lecture coming up on the effects in electromagnetism. So let me state this apparent paradox. But that leads to this funny paradox. So here's what we might be able to do with this. Suppose we do that. If Sally then travels at that speed, so if Sally travels to Alpha Centauri, that's a nearby star, and the distance to it is 3 light years, LT, 3 light years away, right? So if she travels to Alpha Centauri, right, we see her take, well, we can figure out pretty quickly how long this is going to take her, right? She's traveling almost exactly the speed of light, and Alpha Centauri is 3 light years away, so we see her take 3 years to travel. Okay, good. Fine. But then, here's the strange thing. She thinks, or she observes, because of this time dilation thing, that effect that we're just talking about, she observes the trip to take, as far as she's concerned, right, she only aged 1/5 as much. So she sees the trip as taking 3 years divided by 5 equals 0.6 years. And they use this effect all the time in science fiction, right? It takes forever to get to these stars that are light years and light years away. But because you're traveling near the speed of light, you won't age very much, and you won't have died before you got there. So that'd be great. But there's something mysterious here, right? You can't be cheating nature. There's a problem now, notice. Because then what would her effective speed be, right? Does she think then? Does she think then that her speed v is equal to 3 light years? And she's able to cover those light years in only 0.6 years? When you divide, then you'll see you're going to get back our number 5. But the units will be left light, which means the speed. So does she think then she's traveling at 5 times the speed of light? Well, she can't observe herself to travel faster than light, right? Laws of physics are the same in all reference frames. And as I'm sure you're all familiar, in relativity, you can't observe a physical object traveling faster than light. So there's something missing here that we haven't thought of. There must be some way out of this so-called paradox, something we haven't accounted. And that something special actually also you can show to be a direct consequence, and it comes out very naturally when you apply these equations properly. I just don't have time to go through all of that with you in this lecture, but I can give you the basic bottom line answer. The answer to that, of course, is going to be no. And the reason is there's another common effect. It's called length contraction. Right? She should know, right, that she's traveling, and we all agree that she's traveling near the speed of light, right, relative to us. So she knows that her speed is near c, right? And the only way then that she cannot be breaking the speed of light and get there in what she measures right off her watch as 0.6 years must be that Alpha Centauri to her appears to be closer. This is this length contraction effect. And it has to appear to be closer by precisely the same factor of 5, or more generally, that factor of gamma. And that turns out to be the answer. This length contraction effect, what it says is that to traveling observers, and by traveling, again, in relativity, you always have to be careful. Something's always traveling compared to something else, right? So to traveling observers, by traveling, I mean that they are moving past some stationary milestones. So to traveling observers passing, so they can't, we're not talking about them passing something that's moving, or we're not talking about them looking at milestones that are moving along with them. The idea is there's some milestones that are stationary like this, right? So I'll label those here milestones. And then I'm talking about an observer in some kind of a spacecraft whizzing past these at some velocity v. So to traveling observers passing stationary milestones, their observed distances, their observation of the distances between the stones, right? Between the milestones is reduced by a factor of gamma. Once again. So in this case, gamma in our example was 5. So what that means is she could think of like the Earth here is one milestone and Alpha Centauri is the second milestone. And the distance between them, right, when they were stationary, when she was stationary compared to them, and as we see them as stationary observers, is 3 light years. But she's going to see them as moved closer together. The length will be contracted by her factor of gamma or her factor of 5. So she sees herself traveling 1/5 the distance in exactly 1/5 the time, so she agrees with us that she's traveling at that given velocity v. Very good. So these are then the basic effects from relativity that we will need to understand the consequences then of the motion of charges on Coulomb's law, which is what will take up the rest of this lecture.